So in last lecture, we uh, discussed a problem which was a non-holonomic problem and which is popularly known as Chaplin sledge. So in Chaplin sledge, what we did is that whatever we have learned till now, like the rotation of a body in 2 dimensions and how we can get the velocity of a point on a rigid body, and using the angular velocity concept and the relative velocity, uh, we could find the absolute velocity of any point. So basically, this much stuff we did in the last, and we built we built a structure where we can just a second, my mouse is not working. Yeah, so we built a structure of
That
equation.
screen is not visible.
Screen is not visible.
Yes.
Okay. Okay, just wait a second. I will leave and rejoin and see if it works. Is the screen visible now?
Yes, sir. Yes,
Yeah.
it is now. Yes, sir. Is it now visible?
Okay. Actually, I forgot to share my screen. That is why. Yeah. Just wait a minute. Okay, so I was telling that in previous lecture we solved a system which was a non-holonomics with a non-holonomic constraint, and we set the equations of motion for that system, which were looking like this. So with the help of these equations, we can simulate this object, and you can analyze the giving different initial conditions how the behavior of the sledge changes. So in today's lecture, we will just build some more tools which will help us in solving more complex problems. So in today's lecture, I think this is lecture number 15, if I am correct. Yeah. Lecture number 15.
Like number, sir. On YouTube it is 15, but in reality it is 12.
It is no, it is actually 15. So we can discuss it later. Why is it 15, and why there is mismatch? But it is the
Yeah.
lecture number 50. Okay. So uh, in today's lecture, what is our agenda? So let's first uh, try to understand it. So first we will discuss the theory of frames. Theory of moving frames are frames. Okay, so let's have a frame. Uh, let's have a frame and let's assume that this frame is fixed. That is, this is inertial frame. It has zero acceleration. And for this case, let's assume it has zero velocity also. So it is something which is not moving, which is not accelerating at all, which is not rotating. So I call this frame as inertial frame. And let E1 cap be the unit vector in this direction and E2 cap be the unit vector in this direction. So basically this E1 and E2 define this inertial frame are this fixed frame which I have denoted like this. Calligraphic F and subscript F. Subscript F defines the fixed frame and this calligraphic F defines the frame. Let's take another frame. Uh, let's take this frame and let's say that this frame is some E1 dash hat and E2 dash hat. See, E1 and E2, sorry, this E1 hat and E1 dash hat, they are different unit vectors. You can clearly see that this unit vector is pointing in this direction and this unit vector is pointing in some other direction. So obviously these E1, this unit vector and this unit vector are not same. So I have denoted this by E1 dash and similarly E2 dash. And let's call this as this is another frame, but let me call it as body frame. This F is calligraphic F and B means body frame. That is, this frame is fixed to the body. Okay. Uh, at this case, this is not necessary to that it is not necessary for us to call it as body frame because this can be any frame, not necessarily be fixed with the body frame. But in the coming like maybe after few 10 or few seconds, few 10 or 15 minutes, we will see that this frame will be a body fixed frame. So that is why I'm calling it as body frame. So we have two frames. We have E1, E2, that is F fixed frame, and we have E1 dash and E2 dash, which is body fixed frame. And the origin of this is O, and the origin of this is O dash. Okay. So let's take a uh, let's take a vector Q. See, when I am saying I am taking a vector Q, although it seems that this vector is inside the E1, E2 frame, that is body frame, but even if you remove these frames, this Q vector has its existence and it doesn't depend upon the body fixed or the body fixed frame and the inertial frame. Even if there were no inertial frame, this vector would have been there in this direction. When I am saying that there is Q vector, you just make an imagination of an arrow. So there is an arrow which has this much of length and which is directed in this position. So even you are defining this in some different direction, it doesn't matter. It doesn't change this vector Q. So this Q has its own existence, irrespective of how you define the inertial and the body fixed frame. Okay. Now we are saying that this Q has its own existence, but this Q vector we can represent it in this body frame and we can represent it in this inertial frame. Okay. So, but why we are doing this? The reason being that sometimes we know a vector from one frame and we want the vector in some other frame. Okay, we want its representation in some other frame. Or sometimes we may know a vector and we want to calculate its derivative in other frame, but we know its derivative in some other frame. Okay, so this is the reason why we are doing this stuff. So what I mean by saying that it has different representations. So basically what I mean is like this. If I take perpendicular and put it on this axis, similarly this, so this much amount. So this is its component along E1 dash axis. That is the x-axis of body frame, and I will call it as dash because it is in the dashed frame. Similarly, it has its component here, which I will call as Q2 dash. 1 stands for the x-axis, 2 stands for the y-axis. Dash stands that this is in the dashed frame, that is the body frame. So see, so we have this Q vector. We have this Q vector. And we see that in this direction, that is this, there is Q1 dash component. I can define a vector like this, which will be Q1 dash times E1 dash. That is the direction of that vector is along E1 dash, but the magnitude of that vector is simply this whatever is the component of this along this axis. Similarly, I can define a vector along vector along E2 dash as Q2 dash E2 dash. So using triangle of vectors, I can say that our Q is Q1 dash E1 dash hat plus Q2 dash E2 dash hat. So we have now represented this Q in this frame because these are the components along E1 and components of Q along E2. Okay, so first thing which we have got. Second thing is that so this Q vector is here and I can take its component in this frame. I can take the component of this vector in this frame. So what I will do, I will throw the projection of this Q along this axis, and I will throw the projection along this axis. Okay, so let us do it. So let us throw the projection. So what is this?
Sir, 2 dash cos theta. 2 dash,
So,
sorry, 2 E1.
so it is basically the component of Q along
Along
E1.
E1.
So I will call it as Q1. Okay, the component of Q along x-axis in this frame, that is Q1. Similarly, its component along E2 is Q2. Okay, so I can also represent Q, this vector, as Q1, which is the component along this E1 hat plus Q2 E2 hat. Is it clear?
Okay, sir. Yes.
So I have basically represented this vector, which is Q. See the vector Q. I have represented it in two frames, Q1 dash E1 dash plus Q2 dash E2 dash plus Q1. I can define another frame and I can represent it. Although I am representing in the different frames, but the Q doesn't change. So Q has its own existence. This is why I'm telling it repeatedly so that it sits in your mind that Q is something which has nothing to do with the frames. Okay, it has its own existence. Oh, okay. So now let's uh, define. Let's define the derivative of this Q vector. So we define the derivative of this Q vector in fixed frame or with respect to the fixed frame as we sometimes write it like this, or we sometimes write it like this, or we just write it like this. So all of this, whenever you see something like d by dt of q and there is some superscript on the left, or q dot with this denotation, or just simply q dot. These all means that we are taking the derivative of this q vector in the inertial frame or the fixed frame. And what do we mean by this q dot in fixed frame? It is defined like this. Let me define it. We define it like dq1 upon dt e1. I am dropping this cap sign. You should understand that e1 is just equal to e1 hat, and E1 dash is just equal to E1 dash hat. So I am dropping these hats because it is now understood that E1 is some vector. It is not a scalar. It is a unit vector. Okay. So dq1 upon dt plus in the direction of E1 plus dq2 upon dt in the direction of 2. So this is the this is the definition of the derivative of a q vector. So basically what you are doing, you are seeing what is the rate of change of this component and along E1 axis, and also you are seeing what is the derivative of this vector component along this direction. Okay, so this is the definition of a rate of change of q vector with respect to the fixed frame. So now let's define what is the definition of dq upon dt in body frame. So in by the same line as you should understand that this is nothing but dq1 dash upon dt e1 dash plus dq2 dash upon dt. So basically what is this? It is the derivative of this q components in FB frame, that is body frame. So you see what is how the component is changing with time, how the components of this q vector in this frame are changing with time. So that is what we call as dq upon dt. So sometimes what happens is that you know what is the derivative of this q component in this frame. You know what how this q changes in this frame. That's so you may say that when this case happens. So let's suppose that we are on some body, and on that body we are moving along some path which is defined in that frame. So you know how you are moving on that body which is moving, which is not a fixed body. Okay, but you know this thing, so you can calculate from that trajectory, you can calculate the velocity. Okay, but you don't know how you are moving with respect to the fixed frame. So the basic thing is that it will become more clear. So I am just building the tools so that we can use this. So now the thing is that let's assume that we know this derivative. That is, we know how this vector components are changing in this body frame. Can we find out how the vector is changing with respect to the fixed frame? Okay, so this is the question. If we know how the vector, see this vector is there, and when time goes, this vector changes. For example, say at this instant of time, this vector points like this. In another instant of time, this vector points like this. So there is a change in vector, and that change in vector in itself is independent of these frames. But we want that change to define in this frame, or we want that change to define in this frame, like we are defining this vector in the two frames. Similarly, we want the change to be represented in this frame or change represented in this frame. So this is that derivative. Basically, this subscript, no, superscript script represents the representation of those changes, whether you are representing in this frame or you are representing that change in this frame. So let us suppose that we know how this vector changes in this frame. Can you find out how it would change in this frame? That is, we know this. Can you find this? So let us try to calculate that. So basically, we want to find this thing, dq upon dt. And we can do this by saying d by dq. What is this q equal to? This q is equal to q1 E1
One
plus Q2. Yeah,
is a go to into yes.
yeah.
Okay, sir. Okay, okay, fine.
Audio is clear
Yes, sir. Audio is clear.
and the screen is visible.
Yes, screen is also visible.
So I am saying that this Q, I can write it as Q1 E1 plus Q2 E2, which we saw here. This Q can be represented as Q1 E1 plus Q2 E2, or it can be represented as Q1 dash plus Q2 dash. Okay, so I can represent this Q as this, or I can represent it in, so this derivative with respect to the fixed frame, and this q I can represent it as q1 dash e1 dash plus q2 dash e2 dash. Okay, so now what? So I am saying that we know this derivative, and see in this derivative there is e1 dash and e2. So I will expand this one. Okay, because something we know, we are knowing this thing and not this one. Okay, so this is d by dt of q1 dash e1 dash, but in fixed frame. So I can do the product rule. Okay, okay, let me expand it, and then d by dt of q1 dash e1
Sir,
dash.
sir, how you equate dq by dt in fixed frame uh, is equal to the dq by dt in body frame?
What?
As I am saying, sir, uh, how you have equated this dq by dt in fixed frame
Mhm.
with with dq by dt in body frame? Are you
No, no,
just replace?
I
Are
am
you
not.
just? Hmm,
Yeah, I am, see, this is dq upon dt. This vector has its existence, you know it.
yes, sir.
It has nothing to do with trade. I'm just
Yes,
replacing this vector like this q1 e1 plus q2 e2, because this is same as like q vector,
yes, sir.
and I can represent this q also like
Oh,
q1 dash e1 dash plus
yeah,
q2.
yeah.
Okay, this
Okay.
is just a representation of that vector. This vector
Yes,
itself represents that arrow. Okay,
yes,
this is an arrow, and this is also an
yes.
arrow. These are same arrow in the
Okay,
space. So in space, these represent the same. Okay.
okay,
So
okay.
now this d by dt of q1 dash e1 dash in fixed, d by dt of q2 dash E2 dash. Okay, this is also in fixed. Okay, fixed with respect to fixed. So I can take the derivative of q1 dash by dt and taking this as constant. Okay, plus I can take q1 dash as constant and de1 dash upon dt. So E1 is not a constant in fixed frame. So I am taking the derivative with respect to fixed frame. So E1 is not a so if so let's see. If this is attached to a body, the body will move. When the body will move, this frame is attached to that body. So this E1, it will also move. For example, at this point, it is in this direction. Maybe at some other point in time, it will be in this direction. So E1 itself changes in this frame. Okay, if you see in this frame, this E1 will be here, then it will be here, then it. So this is a vector in itself, and it is also changing. Okay. Yeah. Clear?
Okay, sir. Yes, clear.
Okay. So. So it is also changing. So what we will do. So basically I am using the product rule, derivative of this thing times this, and then derivative of this thing times this. Okay. Similarly, we will do this for the second one. And so this will be equal to dq2 dash upon dt e2 dash plus dq, sorry, q2 dash de2 dash upon dt. Okay. So I will assemble these two terms, that is this term and this term. So what is this dq1 dash upon dt e1 dash plus dq2 dash upon dt e2 dash? If you see, this is dq1 dash upon dt e1 dash dq2 or dash upon dt. So basically this is the derivative in fixed frame. So instead of these two terms, I will write what? I will write dq upon dt in body frame instead of these two terms. Plus, then there is this thing dq1 dash d1 dash upon dt plus q2 dash d2 dash. Okay.
Okay, sir.
So these E1 dash and E2 dash, these are fixed to the body, and body is moving with respect to the fixed frame, isn't it?
Yes,
So
yes.
E1 dash and E2 dash, these are two vectors. These are fixed to the body. Okay, this is E1 and this is E2 dash. This body in itself is moving with respect to the fixed frame, for example, with omega b with fixed frame. Okay. If this body is moving with omega with respect to fixed frame, so is this frame. This frame is also moving with the so this frame is also rotating with this omega b with the fixed frame. Now what we are doing, we are basically trying to find out the change in the vector with respect to time, which is fixed to the body, and we have already done this. If there is a vector which is fixed to the body, we know the change in that vector is nothing but omega b omega across the vector itself. We have done this. I hope you remember this thing. So if a body, if there is a vector E, if there is a vector, say this, and the vector it in itself is moving, rotating with respect to the fixed frame by omega, then the change in that vector with respect to the fixed frame is omega times E1. So I can replace this by omega cross E1. Okay. So what we will get is dq by dt plus q1 dash. This is omega b. Omega b with respect to f, but I think that you understand it, that it is with respect to the fixed frame cross e1 dash. Similarly, q2 dash, this will be omega cross e2 dash. Okay. So what I will do next is uh, I will see, since this q1 dash and q2 dash, these are scalars, so that I can multiply it with this or I can multiply it with this. So I will take and multiple it with q1 dash. So I will get omega b cross q1 dash e1 dash plus omega b cross q2 dash e2 dash. Okay. And this will be equal to dq upon dt plus. So I will take the omega and I will cross it with q1 dash e1 dash plus q2 dash e2 dash. So we know that we can do it for the cross product, because if the cross product is like this, we can expand it like this. A cross B plus C is A cross B plus A cross C. Okay, so we can do it. I think this is known as distributive law. Yeah. If
Yes,
I
sir. Yes, sir. Yes, yes.
Okay, I hope it is known as distributive. So what we have now? So we have this plus omega B cross. What is this?
It is Q1. Sorry, Q dash.
So no, it is not
Q,
Q dash. It is Q
only, only,
vector.
only Q vector. Yes, sir.
It is Q vector. Now you can represent this Q vector as Q1 dash E1 dash plus Q2 dash E2 dash, or you can replace it with by Q1 E1 plus Q2 E2, because this is simply a vector.
Yes,
Okay.
sir. Yes.
Okay. This,
Yes.
so we have got a very important result, and that is the derivative of Q with respect to the time in fixed frame is equal to this thing. So dq by dt in fixed frame. Oh, so we have got a very important equation which is very often used, and this is the powerful equation. So what this says that is that the derivative of a vector in some frame is equal to the derivative of the same vector in another frame plus the angular velocity of another frame with respect to the first frame cross that vector itself. So this is very, very powerful equation which we will be often using. Okay. So now we have got an equation which will so if we are able to find the derivative of some vector in some another frame, we can use this equation to calculate the change of that vector in some other frame. So okay, so now let us take some example and see. I need water. So any question?
No, sir. No, sir. Fine.
I hope you are understanding.
Yes, sir. Yes, sir. Alhamdulillah.
So is this being recording? I think it is, yeah.
Yes, sir. It is recording. Yes, sir.
So now let us take a problem. So let's take Just wait a minute. Someone is calling me. I will put a message for him. Uh, so what I was saying. So this is a fixed frame. Okay, this is a fixed frame, and this is its origin. Uh, okay, let me rub this thing so you are not confused that this is 3D. Okay, and let's rub this also. So this is O, and this is E1, and this is E2. This is fixed frame. Okay, and let's take a body, a rigid body. Say this is a body, and this is some arbitrary shaped body. And let's consider a point in this, and let's attach a frame. Let us attach a frame. We glue this frame to this body. Okay, so these E1 dash and E2 dash, these are two arrows which we are fixing to this body. As this body moves, this E1 and E2 also moves with the body. Okay, so we call this frame as body fixed frame because it is fixed to this body. And this point is the reference point or the origin of that body fixed frame. And a point, and there is, let's assume that there is a path. Let us create a path. This is the path, this is a way on this body. So this is the way, and there is a particle which is going along this way. Okay, so we know this path in on this object. We know this path on this object. So we know the position of this particle in this frame. When I am saying I know this path, that means I know the position of the particle. Okay, in this frame on this object on this body. Okay, so this is a body, and this is the position of this P point on this body, and I call this position as R O dash with respect to, sorry, RP with respect to O dash. Okay, so I know this RP with respect to O dash in this. I know this is a vector now. Okay, so R P O dash. This is a vector. Okay, so how this vector has been defined? It has been defined. It has been defined as a line between this O dash and P. So even if you remove this frame and remove this frame, this arrow will be there. Okay, this arrow will be there. So now we can represent this vector in this frame, or we can represent this vector in this frame by taking the component of this arrow in this frame. We can represent it in fixed frame, or we can represent it this in this frame. Okay. First, what we want that let's assume that we know this position of P in O dash. We know it, and also let us say that we know the velocity of P in this frame with respect to O dash. We know the velocity, and let us also say that we know the acceleration of with respect to the O dash, and what we know is that we know O dash velocity or the position with respect to O. So we know this. We know this vector O dash with respect to O. We know also this vector. And we know its velocity. We know its velocity with respect to O dash. That is, we know the velocity of O dash in fixed frame. Okay, we know this vector. And what we want, can we calculate RP with respect to O? So can we calculate the position of this P in this frame? That is, can we know what is this position equal to? What is this position vector? So if I join this, oh my drawing is so good. RP with respect. Okay, can I find this? So the question is that if I know this stuff, can I find RPO position of P with respect to O? Can I find velocity of P with respect to O? Can I find acceleration with respect to O? Okay, so these are something which we want to answer. So let's get started and see what we know. Okay, so let's start and see what we know. So what we know is that RP with respect to O, this vector can be written as this vector plus this vector. I can write RP with respect to O as RO dash with respect to O plus RP with respect to O dash. So I can write this. Okay. So first thing I was saying that if I know RPO dash and I know RO dash with respect to O, can I find RPO? Yeah, I can find. One question which may come into your mind is that we have done this thing before. Is this
Yes, sir. Yes,
question coming to your mind?
sir, I was just thinking about it in 11th class. We are also already done this concept, position, velocity of another frame in the another frame.
Yeah, that is none of that is there, but I am saying that few lectures
Ah, yeah,
before
before
we.
lecturers, yes. Yeah,
So
we
what is
also done
new in
this.
this?
Yeah,
If we
I
have
was
done
just
this, what is
thinking
new?
about.
So the new thing is that this point P, this is not fixed in this frame. Or we can say this RPO dash vector. This is not fixed to the body frame. This vector is in itself is changing in that frame. In previous cases, we were taken a point which was fixed to the body frame, but this point is not fixed. It is moving on this object. It is not fixed to the object. Okay, so there is a difference. So when we have a point which is fixed, we know what are the formula. But in this case, this point is moving on this object, and we want its position in fixed frame. We want its velocity in fixed frame. Okay. So first we got is that if we have the position of this reference point with respect to the fixed frame and the point with respect, so we can just get this vector like this. Okay, so this is the first point. The second point is now we want velocity of P point. So what is the velocity in fixed frame? It is nothing but the derivative of this RP O vector. So this is the velocity of point P, which we want. Okay, we want this thing. We want velocity of point P, and that is nothing the derivative of that vector RP position vector in fixed frame. And what is this equal to? We have just find out that so here the Q vector is this. We know the
Yes,
derivative
so
of
we
Q
are.
vector in fixed frame is derivative of that vector. Derivative of that vector in body frame. Yeah.
Yes, sir. Yes,
Oh,
sir. You can negotiate. Oh,
but before doing this, let us do one more step and then we can do this because we know something. So if we know something, we will utilize that thing before doing it. So what we know, my mouse has stopped working. Let me use my. Okay, so I was saying, so we can write this f d by dt of rp rp with respect to o. This can be represented as, this can be written as r this plus rp with respect to o. Okay, and I can further write it as d by dt of r o dash with respect to o in fixed frame plus d by dt of rp with respect to o dash in fixed frame. Okay, so this is known to us. I have already said that we know the velocity of o dash with respect to o. This is known. So velocity of this reference point with respect to o, it is known. So this is the set of known things. Okay, this set is the set of known things. So we know the velocity of o dash with respect to o. So let me write this. Um, what has happened? Something wrong. I don't know how to navigate through this board uh with my hand. It's okay. So we know this. What is this? This is velocity. Okay. So this is velocity plus d by dt of rp o dash. We don't know this, so I will take this as q vector. And we know the derivative of q vector in fixed frame is nothing but d by dt of q. What is happening? So I know it is equal to d by dt of q vector in body frame plus omega of body with respect to fixed frame cross that vector. Okay, so we have got a velocity of point P is nothing but the velocity of reference point plus the, what is d by dt of RPO? This is velocity of point in body frame. Okay, plus omega a body cross the RPO dash. So basically, we have got a formula and which is saying that, so if you know the velocity of reference point, you know the velocity of this P point in this body frame. So the velocity of this P point in fixed frame will be equal to velocity of this reference point plus velocity of this P point relate with respect to the body frame plus omega time cross with this position vector, relative position vector, or the position vector of the point P in body frame with respect to the frame. Okay, so This is known as 3-point formula for calculating the velocity, which is very important. Okay, so when you will deal with the practical problems, so you will see how many mistakes are made when this formula is not being used in a proper way. Okay, so sometimes
Sir,
you may just, yeah.
sir, is this necessary that the fixed body frame is rotating with respect to the initial frame, or
Yeah,
it may be, sir, it may be, it may have a linear velocity with respect to
yeah.
fixed frame.
So what
So
will be the omega then?
omega will then v v by r. Sorry, omega will be zero. Uh,
What will be
That's
this?
there.
What will be the omega p? It will be just equal to omega dash plus omega p in volume. So this is basically known as, this is a name and it is known as relative velocity.
Yes, sir. So
So
it
the
does not depend on the linear velocity of the body fixed frame.
which,
The body frame.
yeah, relative
Uh,
velocity.
yes, sir. VP. Yes, sir.
Yeah, it doesn't depend because you are seeing from the body frame itself. Okay. So this is known as
Okay.
the, yeah, so this is known as the um this is known as the body fixed frame. Okay. Uh, and the thing is that see what people usually make mistake is that when they have to calculate the velocity of the point P, so what they do is they say that what is the velocity of point, what is the velocity of point in B, add that velocity to the velocity, what is the velocity of reference frame with respect to the inertial. So add these two, you will get the velocity. But you are missing this term, that is the omega cross. So basically, this represents the velocity component of point P, which is due to the rotation of the frame, which is rotating with respect to the fixed frame. If there were no rotation, then this formula was okay. But if the frame is rotating, then you have to add this velocity also. Okay. Okay, so now we have got the expression for velocity. So let us jump and see what is the relation for the acceleration. So if we know what is the acceleration of the P point in the body frame, so what will be the acceleration of the what will be the acceleration of the P point in inertial frame? We are doing this because if we know the velocity of the P point in inertial frame, we can simulate this. We can find the position of the P in body fixed frame. Sorry, in inertial frame. Similarly, if we know the acceleration of P point in inertial frame, we can calculate the velocity and integrate the velocity to get the position. Okay, so this is all well, the reason why we are doing this. So now let us do for the acceleration. So we will use this. We will use this formula to get our acceleration. So what is the acceleration of point P in body in an inertial frame? That is with respect to O. It is d by
A
dt of velocity of point P in fixed frame. Okay, but that is equal to uh, uh, d by, so keep like I on everything because this is very important to think, you can make a mistake. So d by dt of Vp is nothing but velocity of O dash plus velocity of point P with respect to B plus sorry, in body frame omega of body frame with respect to fixed frame cross RP O dash. Okay. So d by dt of VO dash is acceleration of O dash. Okay, this is with respect to fixed frame. Whenever I am not using the superscript, it means it is with respect to fixed frame. So this is the acceleration of d by dt of VO dash is acceleration of reference point. Okay. So plus uh, d by dt of this vector. Okay, let me write this d by dt of this vector. Okay, plus d by dt of this vector. Uh, so acceleration of point P with respect to O is equal to this. So what is this d by dt of VP? Yeah.
Sir,
Uh,
AP sir.
uh,
Sir, A acceleration of P.
so in which frame?
Sir, body fixed frame.
But you are taking the derivative in fixed frame.
So this is equal to VP of body plus omega into VP.
VP of
VP, sorry,
hmm,
VP in body fixed frame plus
so this is
omega
basically
cross the D by dt of that is an AP in fixed frame in body frame plus omega into VP in body frame.
so
Yeah.
basically so this is our Q vector now. Okay.
Yes, sir. Yes, sir.
So the derivative of Q vector in fixed frame is derivative of Q vector. This is derivative of Q vector in body frame. Okay. Plus omega times omega cross that vector. What is that vector? This vector is
VP, DVP.
okay. Okay. So I have used that formula. This dq upon dt is equal to dq upon dt in body frame plus omega body cross this vector. So I am using, I have to find the derivative of vector in fixed frame. So I'm using this formula and I have got this plus. What is this? I will use first let me expand this. So I can write it as d by dt of uh, first vector cross second vector as it is plus first vector cross derivative of second vector. Okay, so what this will be equal to? This will be equal to AP with respect to O is equal to acceleration of O dash plus d by dt of Vp is the derivative of velocity in body frame is equal to acceleration of the point. Okay, in body frame. Okay, plus omega b cross velocity in body frame. Okay,
Okay.
plus d by dt of omega b. So I will call this as omega b dot. Okay, because this is the derivative of omega b. So I have already told you that if I am not using the okay, let me use okay. So omega b in fixed frame. Okay, cross Rp with respect to O dash plus omega p cross. So what is this d by dt of Rpo dash?
Sir, VP in body frame
Yeah.
plus
So
sir, VP in body
so
frame.
it
Yeah, D
is
by
d
R
by
by
dt.
DT.
So it is so Vp in body frame, yeah, plus
Plus omega
omega
in
bar cross
B cross
this
RPO.
vector. Yeah, is this okay?
Yes, sir, it's okay.
Okay, so we are going to get a very beautiful expression which is very known. So be ready. So this is a that shows acceleration of point in body frame plus see omega cross Vp omega cross Vp. So this is 2 times I will write it 2 times omega B cross Vp in body frame. Okay, plus then there is this omega B dot of P plus omega B cross omega B cross.
Sir, you have not expanded the uh, W D omega upon dt with respect to body frame, a fixed frame.
Yeah.
One, two,
So
three, four.
I have just written it. This is important. So I have not expanded this thing d by dt of omega b with respect to fixed frame. Okay, so I am just calling it that it is the rate of change of omega with respect because we are knowing how that frame is rotating in fixed frame. This is what we are knowing. Okay, what is the omega of the fixed frame in sorry, what is the what is
Body
the
frame.
angular velocity and what is the angular acceleration of the body frame with respect to the fixed frame? This is known to us. Only then we can do this stuff. And one more interesting fact is that which I will write at at the end. So that is that the omega b dot in fixed frame is equal to omega b dot in body frame. This may look like strange to you, but this is a fact. Okay. So whether you are taking the derivative of body frame in body frame or whether you are taking the derivative of body frame with respect to the fixed frame, these are same. These are not different things. Okay. Why this is so? You can expect. Okay, let me do it quickly so that there is no doubt in your mind that I am skipping something. So what has happened? Yeah. So see, I will expand this. So omega b, so f d omega b upon dt, okay, is equal to. So let's expand it. What it will be? Omega b in body divided by dt plus omega b cross omega b. Is it?
Yes, sir.
Yeah,
Yes, yes.
because this was the q. So this will be equal to 0 cross product of a vector with itself. So this is why. So the derivative of the omega in fixed frame is same as the derivative of omega in the body frame. Got it?
Yes, sir. Yes.
So now we have a very important formula which says that the acceleration of a point with respect to the origin or the fixed frame it is the acceleration of the reference point plus the acceleration of the P point in body frame plus 2 times this. I will not call what it is, but 2 times this plus the angular acceleration of the body cross with the position vector of the P in body frame with respect to the body frame, not in body frame. This is with respect to the body. This is the definition of the this vector. Representation is something else. You can represent this vector in body frame. You can represent it in inertial frame, but the definition of this vector is with respect to the O dash. So then there is omega b cross this. Okay, so this is known as 5-point formula for the acceleration. So these two terms you understand that this is the acceleration of the reference and this is the relative acceleration of point in body frame. And if you look at this thing, so this is something like let's assume that these are mutually perpendicular. So you will get omega square times r. And what is omega square times r?
Alpha.
No. What I am saying is, what is omega square times r? What is v square upon r? You know this?
This is a centripetal
Yeah,
acceleration.
it is centripetal acceleration.
Acceleration.
So this is centripetal acceleration. At every point, the body, we can assume that the point P is going on the circle. So this is towards this RPO dash. Okay, so this is something like centripetal acceleration. Okay, this is something like centripetal acceleration. Okay, so this is act. So if this is the P point and this is the body frame, so this is our RPO dash. So at every point there is some acceleration in this direction which is given by this. And similarly we have this omega dot which is nothing but alpha times r, something like this. And what is that? That is a acceleration in this tangential direction. Okay, so we have acceleration in this direction, we have acceleration in this direction. Okay, so these two things we understood that this is something which is tangential acceleration and this is something which is centripetal acceleration. And these two terms also we know that this is the acceleration of this thing and this is the acceleration of this point related to the frame. But what is this? This is something which is known as Coriolis acceleration.
Oh, Coriolis is a Coriolis somehow.
Yeah.
Coriolis forcer. I love
Yeah, it is.
Coriolis.
You don't know this, why it is happening, what kind of, you don't know this force and you call it as Coriolis force or the
Force.
Coriolis acceleration. So the best example of this is that if you are on a rotating disk and you will experience a sideways, for example, if you are on a, say, this is a platform and it is rotating about this vertical axis. Okay, so this disk is rotating about. So you are here, say friend A, and there is another friend B. So let's first assume that this disk is not rotating and this A is throwing a ball towards B. So B will, so the ball will go like this and the B will take that ball. Okay, but now let us assume that this disk is rotating. So and there is some another third person. Third person is here, which is outside this disk. So he saw that A threw the ball in this direction and B is taking. So he saw the ball is in going like this. Again, let's say that A is here and B is here, but this disk is rotating. So A throw the ball in this direction. So this man sees that the ball is going in this direction. But see, the ball is going in this direction, but this disk is rotating. So B might have reached here. So what B sees is as if, and A is something like here. What we see is that as if ball is going in this direction, because ball has reached this point and it should reach, and this can be only for the third person which is outside this frame. He has no ambiguity in this because he knows that A has thrown the ball and the ball is going straight. So there is no force is acting on this. But a person which is on the frame, he sees that the ball should come like this. Okay, but since its frame is rotating, which he doesn't know, it seems that the ball is moving sideways. Okay, so that term that see, if we go with the Newton's laws of force, so the ball should come to him in a straight way. Okay, but it is not coming in a straight way. So then there should be a force which is dragging it lateral ways, and that force is this force. But we know that there
Pseudo
is no
power.
such force. Yeah,
Exactly.
there is no such
Yes, sir.
force. And we are just accounting this radial shift by this pseudo force. That is we call this frame as non-inertial frame. Why? Because according to Newton, if there is no force, the ball should move in the straight line, but it is not moving in a straight line. So say
Yes, sir.
for example, we are moving on such we are moving sorry we are living on such a planet which which is going like this. Okay, so if a person is throwing ball, it will not go straight, it will move. So and there is no force acting on it. So how Newton will explain? Newton can't explain, we can't explain. So we are just relying and introducing a new force which is not there, and therefore we call it as a pseudo force or the Coriolis force. Okay, and this term, this acceleration is known as Coriolis acceleration. Okay, I hope you got this.
Yes, sir. Done.
So with this we completed like the theory of frames, which is very important if uh, because most other people get confused with it. If you don't go in a systematic way and if you don't know what derivatives you are referring to and other stuff, I think I have done my best to make it understand to you. But even if there is some confusion, you can go back and listen this 2, 3, or maybe 50 times until you get it uh, correctly. So now let us shift to a very interesting. I don't know whether you will find it interesting or not, but for me it is very interesting. That is known as the 3D rotation. Uh, 3D rotation, or we call it as rigid body. In general, we may say rigid body motion in 3D. Okay, not rotation, 3D motion. Let us call it rigid body motion in 3 dimensions. Till now, we have defined omega and other stuff in only 2D. We are saying that we have a body and it is moving in 2D. Okay, so we have this body and maybe it is moving in this fashion, but it can move only in this z axis. Okay, it has angular velocity only. But now we are saying what we will do.
Sir, sir, I have a question, sir.
Yeah, yeah.
Sir, as we know that Newton's laws are built in inertial frame, that is, velocity should be constant or velocity zero, that is, acceleration should be zero. Then how,
Yeah.
and in non-inertial frame, Newton's laws are not valid, so we take pseudo forces. So then how we are treating Earth as a inertial frame, even it is a non non inertial frame because it has acceleration, sir.
Who told you we are taking Earth as inertia?
Because we are using Newton's law in, in this frame.
We never take the Earth as the inertial frame. So basically, if you see, if we when we are doing the mechanics in like orbital mechanics with the spacecrafts and these satellites, we don't take Earth as a inertial frame. There is a different frame which we take as inertial frame, and that is fixed in terms of the stars. So there are few stars which we know in our galaxy or in our sky in itself. So we know those stars don't change the position relative to our framework. Okay, so they are fixed. Maybe in like in millions of years they may change, but for our frame, for in our frame of time, those stars doesn't change their position, as it seems that they are fixed. Okay, so we take a frame and attach the frame to those stars, and we call that frame as the inertial frame, and not the frame attached to the Earth. The attached frame is not an inertial frame. I think it answers your question.
Okay.
Yeah.
Okay.
Okay, so let's start now with the 3D. So what I was saying. So I was saying that till now what we did, we is this visible? What I am showing to you? Something I am showing to you.
So it is only showing that 3D motion, rigid body motion in 3D only one.
No, no, my video is not visible. I am
No,
showing
no, sir.
some. Oh, I have forgot to put camera on. I think this is. No, my camera is on. You are not able to see me. Are you able to see me?
Yes, sir. Now you are visible.
So till now I was not visible.
So you were visible, but the okay, okay, sir. Actually, I have off your camera. Just to
Oh. So
also on
I
a
am. So let's assume that this is a so this is a fixed frame. This will not change, and this is the body. And till now, what we were doing, that this body could move in this, whatever position it can move, but it can rotate only in this direction. In Z, let's assume that this is a Z axis, so this can rotate only about Z axis. Till now, we were doing this thing, and this is known as two angular velocity in our motion in 2D. Okay, so we were basically dealing, but now let's assume that this body is moving and also it is moving like this. So it has say angular velocity in any direction. Okay. But before doing proceeding, there is one thing. So what we basically want, we want, say for example, there is this power jack, and we want that when this body moves, so can we find the position of this port? Okay, so when it moves, there is some reference point in this body. Let's assume that we know the position of that reference point in this frame. But when it moves, so this vector which is attached to the body, and it represents the position of this uh, desired point which we want related to that reference point, that also is moving in 3D. And this body not only is rotating, but it is also moving like this. So we want that even though it is moving in 3D and also it is going around, we should be able to find the position of this port at every point with respect to this inertial frame. Okay. So what we will do is that we can decouple the motion of the rigid body. How? We can choose any arbitrary point on this body as a reference point. Choose any point you want. let's take the center point of this screen as the reference point. So now this center point is the reference point. So when this body moves, the center point moves in uh, in our inertial frame. And there is also the body is rotating. Okay, but we are only seeing the reference point. So reference point is going there. So there is only translation of the reference point. And there is the rotation going on around that reference point of the body. Okay, so the body is also rotating about that. So if we do this decoupling, that is the motion of the reference point in the inertial frame and the rotation of the body about that reference point. This is enough. This is enough to find out the dynamics of the whole body. That is, you can find any position of any point on this body. Just you know what is the position of the reference point and what is what is the angular velocity of this object, 3D object. So the first thing is that there is a reference point and which is you know, it is just translating. So if you know it, you know it. Okay, so there is nothing new. But the thing is that if the body is now rotating about that point, so how you will find the, for example, if this is a vector of the port of the desired thing, and when it moves, so first it was in this direction, now it moves. So what is now the direction? Okay, so basically we will focus on this thing. If we have some vector and we rotate it by some amount, so what will be the vector? Okay, so this is what we will be doing. So now let's go back to our white screen. So what I am saying, so I hope the problem is clear to you. And
Yes,
one
sir.
thing, yeah, and one more thing I want to say is that the Euler, there is a theorem given by Euler. What Euler says, say this is the body, and this is the initial configuration of the body in this frame. This is how it looks in this frame. Okay. Now I rotate it. So I am basically rotating it about this axis, and this is the configuration. Okay, so I have rotated it about this axis. Okay, and I got this. But I could like also do from this position, I went to this by rotating about this axis, and then I will go like this. So from this position to this position, I have first rotated about this and then about this. Okay, so I have rotated this body about two axes while going from this position, this configuration to this configuration. But Euler says that if you have initial configuration and you rotate it by about different axes, you rotate about this axis, then this axis, and then this axis, and finally you reached to some final configuration. This is initial, this is for example final configuration. You don't, there was lot of rotation is going around this body. The Euler theorem says that there is a single axis, there is a single axis uh, about which you can rotate this body, about which there is a single axis. We don't know what that axis is, but there exists as a single axis that if you rotate this body about that single axis, you will reach the final configuration. I hope you understand this thing. See,
Yes, sir. Yes, sir.
the
Instead of going to the different axes,
yeah,
there's only one
intermediate
axis.
axis.
Yeah.
Yeah, it is showing some complex motion, some complex rotation, but from first to the final position. So initially it has this configuration, it moved some complex way, and it went and it is like this. So what Euler says that you need not to go through these complex things. Just know it is first configuration and second, the last configuration, there exists a unique axis. If you take this body and rotate about that axis, okay, you will get your final configuration. Okay, just wait a minute.
Okay.
I will come back. So so now let's go back. So let's solve a problem. Uh, let's solve a problem. Let's take a rigid body. Let us take a rigid body. It is in 3D. Okay. And suppose this is our reference point, which I will call as O dash. And let us suppose that there is some point P which we want to track. This is point P. OK. And say this is the position vector. Um, um,
RPO dash.
just wait a minute. Um, so let me call this vector as or not. OK, so this is the position vector of P with respect to the O dash, and I am calling as or not. This is the and there is some ECI frame. OK, there is some ECI frame. Sorry. So I am basically working on satellite, and there we use the ECI frame, and that is why it come to my mind, which is an inertial frame. Okay, this is the inertial frame, which is fixed frame. So, and this body is rotating. Okay, and I am saying that at some instant of point, let's assume that the P point with respect to the reference point, this is the vector. Okay, or not. When I am saying this is the vector, basically there is an arrow which is in 3D going from O dash to P. Now, when this body rotates, so it rotates complex way, I don't bother. But when it reaches to the final state, it will reach to the final state, obviously. And I know that when it reaches to the final state, and let me assume that it is only rotating about this O dash, okay? We can see there is all omega about any point, and the omega is something which is determined by the body with respect to the fixed point. It is not something related to the individual points on the body. So when I am saying it is moving around O dash, it is also moving around P with omega, with same omega. Okay, but for this time, let us say that it has omega. It is rotating about this reference point. So and it has reached to some new point, a new configuration. So when it has reached to some new configuration, so from this configuration to the new configuration, from Euler's theorem, I can say that it has rotated by some angle about that unit, about that single axis. I will call that single axis as n. Uh, so I will call. So I will call that axis. Okay, I don't know, but Euler says that there exists an axis that will take you from the initial configuration to the final configuration. Okay, it does not need to rotate about some arbitrary axis. Just rotate it about some n, about some axis. You will get to the final configuration. Okay, so let's assume that this vector which was initially here and this body gets rotated through some angle theta. Okay, so let's take this as the line, and let's assume that this body has rotated about this axis. So this p will also, this vector will also rotate about this n, and this will reach where? This will reach here, p dash, and this r naught will go from this r naught to that r. Okay, I will call this as r. From O test. So basically this R naught vector has got rotated about this n axis through this angle theta. And also there is one more important angle, that is this R naught will have some angle with respect to this n. I will call that angle as phi. Okay. So what is our objective?
Sir,
Our object,
sir,
yeah,
wait.
yeah.
Uh, phi is angle between R O and n cap,
Yeah,
and theta is actually a 3D angle. Not 3D, but in if I take x and y, uh, somehow the coon, the
yeah, yeah,
p and yeah, coon angle. Yes, sir.
yeah.
Okay,
It is making a cone, and the phi
coon. Yes,
is
sir.
that cone angle. Okay, and theta
Yes.
is that how much it has swept. Okay, the angle. So the
So
Euler
between the
says,
area.
yeah, the Euler says that this body needs to be rotated about this n vector by some theta to get to the new configuration. Okay, so that is the theta,
Position.
how
Yes, sir.
much we are rotating it about n. And this phi is the angle which this r naught makes with phi. And this will remain constant during this rotation, it will not change. Okay, even if you see that r vector that has this same phi making with the n. Okay, so basically let me show you here. So for example, are you seeing these two pens?
Yes, sir. Yes.
So let's say that this is our R naught. Okay, this is our R naught, and this is fixed to the body. So uh, now Euler says that move this body about, rotate this body about some vector n. So I am taking this vector n. This may not be like this. This may be in an arbitrary direction. I don't know. Depending upon the initial and the final configuration of the body, this n is determined. So let us assume that this n is in this direction. This is our R naught and this is n. So this angle is phi. Okay. Now what I am doing? So Euler says me rotate this body about this n. That means each vector attached to the body will get rotated about this n vector. So I am now rotating this. So rotate this r naught. And when I am saying rotate this, how much you have to rotate? You have to rotate theta. So this angle, if you join this tip to this, that radius will move. That will be the theta. Okay. So this is going to theta. But this, see, the new position of this is r, because this is a different vector. See, this is r naught. When it has moved to this, you may say that this r naught has moved, it has just rotated, it cannot change. No, this is, see, the vector changes by changing the magnitude and direction. So this r naught has not changed its magnitude. It was r naught here, magnitude is r naught still here, but the direction has changed. Here it was in this direction and here it is in this. So this is r naught, this is our n vector. We are rotating this about this vector. Okay, n vector. And if you close this, if you put a perpendicular, so that perpendicular is tracing a circle. Okay, and you can get a cone if you have full rotation. But I am not making a full rotation. I am just saying that it is moving only theta. So basically it is moving theta. Okay. Is it now clear?
Yes, yes, it is clear.
Okay, so what is our objective? Now, objective is that you know initial position of P. That is, you know this vector. The initial position of P with respect to O dash, you know, and that is R naught. And you know that you have some axis of rotation. You know that you are rotating your body about some axis. And you also know that you are rotating about that axis by theta. So this much information you have. Can you get what is the new position of P with respect to O? That is, can you find this position vector R? So this is our object. Given these three things, given that you know the position of P initially, you rotated the body about some axis n by theta. Can you find out the new position vector of P with respect to O dash? That is R. So this is our objective. Okay. So yeah.
Nothing, sir, nothing.
Okay. So let us do some geometry. This is not something like this is just geometry, and we will get the answer. So let me let me redraw this and get better image. So this is our R naught. Okay, this is P, and this is our axis of rotation, which is N. And let us draw a perpendicular, and we know we have to rotate this vector. We have to rotate, and this is phi. Okay, so this is phi. And we have to rotate this R naught vector about this axis. Okay, so when you are rotating, this R naught should rotate about this uh, n vector. So by that you mean, and I am rotating this vector by theta. So when it will rotate, okay. So this radius vector will this vector will go to this. Okay, so this is theta. So this P will reach to P dash, and the position of that P dash is something I call as R, which needs to be found. So we need to find out this R. Okay, so how we will do? So if I complete this, this will be some. If I complete this rotation, so this will be something like this. Okay, so this point P will go around in a circle around this N. Okay, okay. So the plane of the circle will be perpendicular. The plane of the will be perpendicular to this. Okay, this radius vector will be, so the circle will be perpendicular to the N vector. So what we need to do, we need to find out this R. What is given? R naught is
Sir,
given
this is
N.
okay, okay, sir.
Yeah. Any question?
Sir, if we cross multiply the position of the P with the P dash, the resulting vector will be n cap. Am I correct, sir?
If we multiply what you are saying, if we multiply
If we
this
multiply the
R,
not this R, no, not this R, sir. The
then
perpendicular distance from the n to the P, that
okay,
is
so
R, R. Yes, yes, yes.
this, okay,
Yeah, with the new position, with the new P dash.
okay, so this
The resulting,
cross
yes.
this.
Theta we know, R we know.
So what we will get for, you are saying that we will take
Yeah,
cross product of this and we will take cross product of this. So this will be something which will be in the plane of this circle. But what will that
yes,
give us? No, no, that will not be. I'm sorry. That will not be. That will be perpendicular to this vector, and that will be perpendicular. So that the plane which will be defined by the R and this vector, and that will be perpendicular to that. And we don't know what is that what is the direction of that program? We don't know, so that is of no use. And also, like we have to calculate R. Okay, so but it is if you can work out this. I would like to have to give you this as a homework problem, but I know like there are some issues, so I'm otherwise I have given. I think I have explained it in a better way, so you know what you have to find. It is now only playing with the equations and the geometry, you will get the answer. But okay, now let us proceed and see how the things goes on. So we need to find out this vector. Okay, we need to find out this R vector. We are given this vector, we are given this vector. So let me do some geometry. I will put, I will do this thing. I will do, this is B. Okay, so this much amount of geometry I will do. And I will do one thing, I will call this as O double dash, because this is already O dash. Okay, so O double dash is this point, center of this circle. Okay, this is O dash. So can I write that my R is equal to R naught plus PB plus PP dash. Can I write this? Yeah.
Wait,
Hello.
wait, wait a minute, sir. R is equal to R not.
So I am basically adding this vector, and this vector using the polygon law of vectors. So if I am adding this vector and adding this vector and then adding, this becomes a polygon, isn't it? The closing side of the polygon, that is R, is nothing but the addition of other two other vectors. This vector plus this vector plus this vector. Okay. Or you can also do it by triangle law of vectors. See R naught plus PB vector. This will give you this vector, that is O dash B vector. Then O dash B vector plus BP dash vector will give you this vector. So that is this thing.
Got it. No, got it.
Okay.
Okay, okay. Okay.
Okay. So okay. So this is understood. So let's do some more thing. So now let me define a vector. Let me define a vector. How I can define? Okay. So let me define a vector like this. I'm defining a vector R n cross or not. So can you find out what is the direction of this? Okay, so let me see what is. This is magnitude of n is 1. Magnitude of R naught, say it is R naught. And the direction of this thing is perpendicular to this R naught and n vector. So basically, it is perpendicular to n, means it is somewhere on this circle. Okay, because perpendicular to n means anything on this circle, isn't it? Maybe it is this vector, it is this vector, it is, but it needs to be on this plane. But it also needs to be perpendicular to what? R naught. So you can see the perpendicular to R naught and in the plane. So this is only this tangent. Okay, so this vector n cross R naught so this n cross R naught is a vector which is like this, which is in the direction of BP dash. Can you get it?
What's that?
Yeah. Huh? Can you get it? I am saying that this n cross r naught is a
Yeah,
vector.
so it is a tangent perpendicular to the n cap.
Yeah, so it is perpendicular to n cap
Also
like
or not.
this, and also r naught. So it is tangent at this point, and it is in this direction, bp dash.
Yeah,
So
yes.
can you tell me what is the radius of this circle?
So O dash P,
Yeah,
O dash P.
O dash p. Yeah, but what is that? O dash p is not something which we know. Tell me in terms of known quantities.
Known quantities.
Do you know this?
Or not.
This is or not. Do you know this? This is
Yeah, we
phi.
know phi. Sir, yes, sorry,
So
sir. R
so
is
what
equal
will be
to,
this?
yes, sir. L is equal to R. Phi is equal to L by R. L is equal to R phi, sir. R phi.
No, no.
Or
This
not phi.
you cannot approximate it by circle. So this is not a circle. So this is perpendicular. This is some base and this is hypotenuse. So you can say
Then
that O double
sign
dash
of
P is R naught sine of phi.
or
Okay.
not sign phi. Okay.
So the radius of this circle is R naught sine of phi. R naught sine of. So you can say that this vector, that is n cap cross r, the magnitude of that vector is the radius of this circle. Are you getting this thing?
Repeat. Magnitude of
See, what is n cross r naught? It is magnitude of n, that is 1. It is magnitude of r, that is r naught. It is sine of the angle between two. What is the angle between n and r naught? It is phi. So sine of phi. And there is
magnitude of
some direction
tangent.
which we know it is this direction. Let's skip that direction. So, but what is the magnitude of this vector? It is r naught sine of phi.
Yes,
And what is r
yes, yes.
naught sine of phi? That is the radius of this circle.
Okay.
Okay, so
Got
that
it,
is
sir.
what I am saying. So the radius of this circle is the magnitude of this vector n cap r naught. Okay.
Yes, sir.
Okay,
Yes.
so I need to find out this BP dash. Can you tell me what is the magnitude of this BP dash? Just magnitude. In terms of the radius of this circle. What is this BP dash? It is
This is
the
B.
radius sine of
Yes, sir.
theta.
R times sine theta. Yes, sir.
Okay,
Radius of
so
R.
okay. So let me say that this
And direction is same.
BP.
And
Yeah, that is. So BP magnitude, just magnitude, it is equal to a radius, and radius is nothing but r naught sine of phi.
theta. Sorry,
Okay,
phi. Yes,
and
sir.
okay.
Theta.
No, this is the radius of this. This is this
Okay.
radius of the circle.
Okay. Yes, sir. Into
Okay,
sine of theta.
sine of theta. Okay, and we
Yes.
know. So this is basically what is this?
Mag-
This is
Magnitude.
this is the magnitude, and what is the direction? Direction is same as that of
And
this vector.
tangent.
Okay,
Yes.
so I will call that in this direction there is some let me call as C, right? Okay, let me call this direction as C. So R naught sine. So what is this R naught sine of I C? This is n cross R naught.
Yes.
So n cross R naught. Okay, sine of theta. Okay, so we have got BP dash vector now. This is not something magnitude. This is vector. Okay. So we have got BP dash. What about PB? PB, this vector, PB vector. So PB
PB
vector.
is
So for this, what I will do, I will define another vector. Okay.
it
So
is
what?
radius minus r cos phi.
Yeah. But
Radius
see,
minus radius cos.
yeah. Obviously. So it is radius minus r cos of theta. So it is something like r1 minus cos of theta. Yeah. the magnitude. Yeah.
Yes. Yes, sir.
Okay.
Yes.
But the thing is of direction. We need it in direction wise. So what I will do is I will define a vector n cross n
N cross N dot R naught.
cross.
Yes. R naught.
Okay.
That is the
Okay.
direction of this. Yes.
So what is this direction? So let's see what is the direction of this thing. N cross R naught. So n cross R naught is this way, and n is something which is perpendicular. Okay. So if you take
Yes.
n cross this, so that will be the direction in this direction. Okay. That will be something which is in this direction. Okay.
Okay. Okay. Okay.
Okay. So let us see what is the magnitude of this vector. First, let us see what is the magnitude of this vector. Okay. So,
Yes.
so what is the magnitude of this vector? R naught sine of phi, isn't it?
Yes, sir.
What is the I should call this as radius. This will otherwise create some problem. So what is the magnitude of this vector? This is 1. What is the angle between these two? That is 90. So what is the magnitude of this vector? This is R naught. So basically the magnitude of this vector is also the radius of this circle. Okay.
Uh,
And
circle.
only,
Okay.
oh yeah, so this is the radius, and the direction is good, which is in PB direction. So only thing is that this PB vector has magnitude which is radius 1 minus cos theta. Okay. And the direction is something in this. Oh, just a wait a minute. So something in this direction. Okay, I will call this direction as let's call it as T cap. Okay, so this is in the direction of T cap. So basically this is also T cap. Okay. So what is this R naught sine of theta T cap? This is n cross n cross R naught. 1 minus cos of theta. Okay, but if see uh, r naught sine of theta, this is the radius of this circle, and you said that this BP magnitude is 1 minus cos of theta into that radius. So this and the direction of this PB is in I call it as T. Okay, this direction I call it T. So this is what is PB. But I know that R naught sine of theta T. So sorry, this is not sine of theta. This is sine of phi. You didn't mention. This is sine of phi. Okay. So R naught sine of phi times T. R naught sine of theta times T. What is this? This is n cross R naught. So this is n cross R naught. 1 minus cos. So now we have everything. So we can write now R. So we can write R equal to R naught plus this PB. What is PB? This is n cross R naught 1 minus cos of theta. Okay. What is this BP dash? It is n cross R naught sine of theta. Okay. So the objective was that if we know the initial position, that is R naught, if
Or
we
now
know
we
n and we know theta, can we find out R? Yes, we have found. We have this theta, we have this n, and there is nothing else. Okay, so we have found out R. So we have basically found a function. We have found a function R which is function of n, which is
Depend on
function of theta, and which is, so you give n, theta, and r naught as the input to this function, it will return you the new rotated r vector. Okay, is this clear? But this
yes,
is
sir.
something which is not that much useful. So we will keep doing something till we reach a point where we will get some nice equation which will be easy looking. Yeah. So what I will do is,
Sir, sir, how
yeah,
much time it will be?
I think within 10 minutes we will finish.
Okay, okay,
Okay. So
okay, okay.
R naught is equal to R naught plus. So this is that three cross product of three vectors. So I can write it as that. I hope you know this thing. You have not.
Yes, sir. Back minus cab. Back cab.
Yeah. Yeah. So using this, I will expand this. So this will be equal to n cap. N cap dot R naught minus n cap dot sorry, R naught n cap dot n. Okay, and whole is multiplied by 1 minus cos of theta plus n cross of R naught sine of theta. Okay, hope I am doing correct. I don't know. Let me check if I am doing correct. Okay, let us.
Yes, sir. It is.
So what is this? This is equal to 1 and dot n is 1. So I can write this as r equal to r naught plus 1 minus cos of theta. This is n and this is n dot r naught. Yeah. And minus r naught 1 minus cos of theta plus n cross r naught cos of theta. So this will be equal to 1 minus cos of theta n dot r naught. See, minus r naught and r naught, these are cancelled. And r naught times cos of theta, I will write it as r naught cos of theta and plus, then there is this cos of theta times n cross or not. I think somewhere I have made a mistake, but let me check it. If I am correct, then it is okay. If not, then I need to look it.
Oh, so it is correct, sir. I think.
Okay. So it is not sine, it is not cos theta, it is sine theta. See,
Where?
from this to
Where?
this, it is sine theta, and
From.
this is sine theta. Okay, these are sine theta. So yeah, we have reached somewhere. So we can just write it in a nice way, and we are done. So I will write it as R equal to, let me write what I should write. Uh, Okay, let me multiply this and I will get n dot r naught. Okay, and I will get minus cos of theta n. But I think I am. No, I think this is okay. Why I should do this? So I have r, which is equal to 1 minus cos of theta n plus cos of theta I plus sine of theta dotted with r dot. So this is known as rotation tensor. So the what is r equal to? It is just r dot r naught. Okay,
Sir,
so
sir, what is this? What is middle term? Cos theta dot.
I will explain. So basically, I have somehow turned this into this equation. Okay, so I have forced this. So I have used the concept of diodes, which I have previously explained in the previous lectures. So what was this? This was 1 minus cos of theta. So this is 1 minus cos of theta. This is something scalar. Okay, this is fine. Then there was some n times n dot r naught. So I pulled out this r naught out, and I know I can put these two vectors side by side. And then when I take the dot product with a vector, I know how the operation takes place. Basically, it takes place that the second vector is dotted with the vector itself, and then that gets multiplied to the first vector. So this is the definition of diodes. So from the definition of diodes, I could write this in this fashion. Okay, is this okay?
Okay. Yeah, yes, okay.
Similarly, so what was here? It was cos of theta. Okay, and I want something like this. That is, I want a tensor which I will dot with r naught, and it should give me r naught. So I want something. Okay, let me. So I want something, some diode or some tensor, which I will dot with r naught. It should give me r naught. That is known as identity tensor, because it doesn't change the vector. Okay, it is not changing the vector. So this is basically the identity tensor. So when you will dot the vector with this tensor, it will not rotate this vector at all. Okay, are you getting my point? This is I will explain in maybe in next lecture when we will see what this I is. But from in this point, you will just know that this is just we are packing two vectors close to each other side by side, so that when we take the dot product of those tensor with r naught, it will return you this r naught. Okay, and sine of
Okay.
theta. Similarly, here it was a cross product, and I changed it into a dot product. Then this is known as skew symmetric tensor or matrix, you may call it as, associated with vector n. So you have basically vector n, which is just a 3 by 1 column vector. Okay, I associate a matrix. From this n, you can create a 3 by 3 matrix, which will change the cross product into a dot product. Okay, so this is the skew-symmetric matrix associated with this n. And this whole is something which is like which contains the vectors only. So this has its own existence. You can represent it in different frames. It will have different components in different frames, but uh, it has its own existence. Just like you have a vector in 3D, it is like an arrow. You have a tensor. I don't know what is the shape, but it is some geometrical object in 3D which transforms your R naught to some other vector. Okay, so this R rotation tensor, it is just like a vector. Okay. But when you are dealing with some frame, you will take it as the components. Okay, so you have 3 by 3 matrix. I think with this, I shall call it a day and we will end today's lecture. I think in next we will continue from this and we will see what actually this R tensor is and how we what this symmetric matrix and how we will build that. And then finally we will see how we can use the Newton's laws or the angular and linear momentum balance in 3D with this rotation, okay? And how we can get the different, we can get different things. So if you have any question, you can ask, otherwise we can stop and proceed from next. Okay. So any question?
No, no, sir.
No question. Okay, so we will meet in next class and we will proceed.